The explosion in bandwidth from video, cloud, and mobile broadband is putting optical network operators under pressure. They need to shift gears to maximize the capacity of every fiber in the network while keeping costs down. But fiber capacity is fundamentally limited by the laws of physics, which set a specific maximum capacity for every fiber in an optical network. Operators need to optimize their networks by trading off the capacity and reach of DWDM wavelengths, and they need to perform this balancing act within one flexible and fully programmable optical interface. But how do we get there? As silicon technology advances, more processing functions can be integrated into a single chip, supporting higher and more modulation formats. Simultaneously, the clock speeds increase, allowing faster processing of complex digital functions and a higher signal baud rate. These improvements directly affect the capability of coherent digital signal processors. Coherent DSPs determine the performance of DWDM wavelengths and ultimately the capacity of an optical fiber. It's like riding a bike. Imagine the drivetrain of a multi-geared bicycle. The rear wheel cogs are like the modulation formats supported by a coherent DSP. They determine how many bits are encoded per analog symbol, whereas the front cogs can be thought of as the baud rates, which determine how rapidly these symbols are transmitted. It's the unique combinations of rear and front cog, or modulation format and baud rate, which allow the network operator to optimize wavelength capacity and reach across any network terrain. So in an optical network, when distances are short and the terrain is smooth, the right gear can maximize wavelength capacity. But when distances are longer and the terrain is challenging, shifting to a different gear reduces wavelength capacity to transmit a signal with much longer reach. Numerous gears in between allow a fine adjustment of capacity versus reach, optimizing wavelength performance. Such flexibility can only be achieved with a state-of-the-art programmable DSP, such as the Nokia Photonic Service Engine 2 with super coherent technology. Its wide selection of modulation formats and baud rates combine to create a super coherent drivetrain, which gives operators the gears they need to flexibly trade off capacity and reach and achieve peak performance over any distance. The new wavelength capabilities enabled by the PSE-2 minimize cost per bit per kilometer, maximize capacity, and advance the capabilities of new and existing optical networks. Network operators can double their metro DCI capacity with a 400G single carrier wavelength. 500G superchannels can be built from just 2 optical carriers, maximizing capacity over both metro and regional distances. Network operators can dramatically increase the unregenerated reach of single-carrier 100G wavelengths to support ultra-long-haul and sub-sea links. And for the first time, 200G wavelengths can achieve true long-haul distances, doubling backbone capacity. As we approach the limits of fiber capacity, Nokia Photonic Service Engine innovations will continue to deliver a flexible, super coherent drivetrain, preparing network operators for the road ahead, giving them the right gear to capture the opportunity in every fiber.